Looking back to our catalog of forces, our treatment of the spring force treated the spring more or less as a one-dimensional system, meaning the spring was treated as if it was a line that can elongate or compress. In the real world, we have three-dimensional objects. We call these extended bodies for the purposes of our class that have surface areas and volumes, and those real objects can deform. They can elongate, they can bend, they can volumetrically compress and expand. And so there's uh, three different kind of corollaries to the spring force that we can use to try to understand how an object will deform when a force is applied over its surface area along different types of directions. We'll start with just elastic deformations. That's basically elongating or compressing something along its length. So let's imagine you have some object. It's a cylinder maybe, and it looks like this. If you were to pull on the ends of this object with some pulling force, the object you might expect to increase in length. So it would expand, right? Something like that, where the expansion could be measured in terms of the increase in length. And so this looks very similar to the spring, except that now our object is not one dimensional, it's three dimensional, and it has a cross sectional area that plane perpendicular to the direction that the force is applied here. Um, the way this works will look very similar to Hooke's law, but instead of just being force that you apply the force over an area. So a comparison of the force applied to the area will be equal to a constant. So instead of the spring's constant, we now get someone's name. This is called Young's constant. So elastic deformations get a named constant multiplied by the change in length over the original length. And so provided you know one, two, three, four of these five quantities, you can figure out the fifth. So that's an elastic deformation. The Y constant is called Young's elastic modulus. It's tabulated for different materials. So it's a physical property of the stuff. Another way an object can deform is you can have something that looks like, we could do the same thing again, I guess. Take that same cylinder. But if instead of just trying to expand it along a given direction, you can apply a set of forces that tend towards rotation. And this will cause objects to shear. This is a shear stress. Oh, real quick, in all of these things, the F over A part, that's kind of like the cause, is called the stress. So stress, force per area applied to an object, leads to strain. The deformation is the result, and that's called the strain. So stresses cause strains. So this is a shear stress, and it will cause a deformation that would look like this. So this is a bending type deformation, where here is the original position, right? And you can measure, in this case, how far you deform laterally. And we'll call that delta x. And we'll still call this L naught. All right. And in this case, um, instead of having Young's modulus, you have the shear modulus, and the equation looks exactly the same. So force applied over area will be equal to, in this case, the shear modulus multiplied by the shear stress, which is the lateral deformation, over the original length of your object. Finally, you can have a bulk deformation if if you have a box, volumetric box, something, I don't know why it's not drawing well, right? That box will have some volume and it has a surface area. If you basically put that box in uniform pressure, pressure is actually measured also in terms of force per unit surface area, such that the pressure is either pulling or pushing, either you put it in a vacuum or a high pressure environment, on all of the walls equally from all directions. That's something known as isotropic, right, etc. Then the entire volume of the box can be compressed if the pressure is higher and pushing inward, or expanded, for example, if you put it into a vacuum. Um, and so the way this works, same type of relationship, the force applied to your object over its surface area is then equal to the bulk modulus of the material multiplied by the change in volume of the whatever it is divided by the initial volume without the, so that's the basically the volume the thing would apply without any of the stress applied. So it's a volumetric strain, and that's stress and strain.